Okay, so in this video I want to introduce calculus. So calculus is a very fancy word to people who don't know it, and it's not a very fancy word to people who know it. So what is calculus? Well, let's start with some maybe basic problem. So let's say you have a car. Let's maybe draw it. This is your car, and you move, let's say, 100 kilometers in maybe 2 hours. The question is, well, how fast did you go to travel that? Well, you can tell me that the average velocity, so average velocity is just the distance divided by the time. So I traveled 100 kilometers, I did it in 2 hours. Well, I must have traveled 50 kilometers per hour. But of course, in the real world, that's not how it works. You may have traffic lights, you may have highways where you can travel more than 50 kilometers an hour. And so the average velocity doesn't tell you much about what actually occurred on the journey. So maybe another example is, like, let's say you have a ball and it falls to the ground, and you could do the same thing. You could ask, well, how fast did it fall? But maybe you want to look at the time where it was halfway and then ask, what was the speed here? So what was the speed of the ball at this point? And this is now a problem of calculus. So calculus gives you a way of determining not only average velocities, but instantaneous velocities. So calculus is actually broken up into really 2 parts. The first one is differential calculus. And differential calculus is where you're calculating things called derivatives and whatnot. And these things are related to velocities and movement. So if something moves, calculus should be involved. So maybe we'll just link to a jargon term, derivatives. So the idea of a derivative is a notion of a slope that generalizes the notion that we're familiar with. In terms of y equals mx plus c, the slope is m. The other branch of calculus is something called integral calculus, and this relates to computing areas under curves. So suppose I have a function and I want to figure out the area bounded below it. Well, integral calculus can give me that. It also gives us a way of evaluating infinite sums and is related to that. So what I want to do today is focus a little bit on differential calculus and give some idea of the definition of a derivative. So let's start by considering some function. We'll just consider it to be nice and smooth, so something like this. Let's say I want to see how the slope is going. Well, we see that the function is generally going up. So its slope is somewhat positive. Here it's positive. Here it's negative. There's a point roughly around here where it's about 0 before it starts climbing up again. Goes to about 0 there and then goes down. So let's see what we can do. Well, let's fix a point. Let's call this x. And then we'll just choose some other point, maybe over here. And we'll just take it to be a distance of h away. So we'll look at the corresponding values of the function. So this is f of x, so y and x. I should actually just write f here. So now if I put x into f, the y value is f of x, and if I put x plus h into f, I get f of x plus h. And so what I can do is I can do something rather silly, and that's connect the 2 points by a line, and then look at the slope of this line. Well, that's just going to be rise over run. The rise is this one minus this one. So what we'll have is f of x plus h minus f of x. And then what we can do is look at the run, but that's just x plus h minus x. So that's just h. Okay, so now we get an approximation of the slope. So notice that this is an approximation of the slope at x of this function. But we could get a better approximation for the slope if we made h a little smaller. So let's say we took h to be this far away. So now this is our new x plus h. And now it gets even better. The approximation is better and better the smaller h goes. So ideally you would want to make h as small as it can go, but it can't be 0 because then we will just have 0 over 0. So what we can do is we can use our understanding of limits. And so what we'll do is we'll define the slope of f at the point x. This is equal to the limit as h tends towards 0 of f of x plus h minus x all divided by h. So it's in some sense the best approximation of the slope given by the rise over run formula. And so what we do is we often don't want to write slope of f at x every time. So what we do is we denote this by f prime of x. Okay, let's rush through an example to see if this idea makes sense. So consider the case when f of x is equal to mx plus c. Then we already know the slope is m. So let's check what happens if we plug it into this formula. So what do we end up with? Well, let's choose a nice color. Let's do this one. We'll have that f prime of x is the limit as h tends towards 0. Now f of x plus h is now m x plus h plus c. And then I've got a minus f of x, so I'll have an mx plus c. And then according to the formula, I divide by h. So let's maybe simplify this expression. So I'll have the limit as h tends towards 0 of mx plus mh plus c, and then minus mx minus c over h. But now observe that the mx's will cancel, the c's cancel, and I get mh over h. But now the h's cancel, and so I have the limit as h tends towards 0 of m, but this is independent of h, so we get m. And that's exactly what we'd expect. So this formula is often called differentiation by first principles. And so when you think about it, the construction and definition is very intuitive. It's something that you would naturally expect. So if you want more practice of these, please look at the other videos on differentiation, in particular the differentiation by first principles. And if you like this video, please hit the like button. And if you're new to the channel, please consider subscribing. If you have any questions, leave them down in the comments section down below, and there'll be notes to accompany this video in the video description.